Let's talk about the trends of acidity of substances. This is going to be a little bit qualitative in nature, but there's going to be some parts that are quantitative as well. So if you look at the periodic table and you focus on rows, you may ask the question, what happens to the acidity of an element as you do go and scan the table from left to right? And in order to answer that question, you have to look at the corresponding acidic substances for each one of those elements, right? So here we have H2O going to HF, H2S going to HCl, you have HBr, HI. And what you kind of tend to see is that when you go from left to right, right, so if you focus on water and HF as well as H2S and HCl, the pKa's, which are shown right here, so the 15.7 that's the pK of water, the 7.0 is the pK of H2S, and so on and so forth. The superscript you see here is the charge of the central element, right? So oxide has a charge of 2 minus, fluoride has a charge of 1 minus. So what you see in terms of the pK is that going from left to right, the pK tends to decrease. And the reason it's decreasing is because the central element has an increase in electronegativity. So you increase the electronegativity of the central element, automatically you make it easier for the H plus to take off because the electrons are going to be involved and much more likely to interact with the central element than with the hydrogen. So removing those electrons away from the hydrogen make it easy for the substance to lose an H plus, which in turn makes the substance acidic or more acidic. So electronegativity for your binary acids is the reason why going from left to right, you have an increase in electronegativity, an increase in acidity. Now, when you look at the trend going from top to bottom, something slightly different has to be accounted for. When you go from top to bottom, and let's focus on the halogens for this discussion. So if you go from HF to HCl to HBr to HI, what you see happening to the pKa's is that they become smaller, smaller, and even smaller as you go from top to bottom. The same trend can be observed for water and H2S. You become a little smaller in terms of the pKa's. And the reason the pK is decreasing going down is not because of electronegativity, because if anything, the electronegativity is going down from top to bottom. So if anything, the pK should be going up. So it's not electronegativity that's ruling the acidity of the compound when you look at the trend from top to bottom. It's actually the size of the central elements. Fluorine or fluoride is smaller than chloride. Chloride is smaller than bromide, and bromide is smaller than iodide. And the reason that matters is because as the element becomes larger in radius, the distance between the hydrogen and central element bond becomes longer and longer and longer. And so the interaction of the hydrogen with the central element is actually weaker, weaker, and weaker. And having the H-X bond becoming weaker is the same thing as saying that the H-X bond is going to break more easily, which means that you're going to produce that H plus with much more, with much easier extent than if you were closer to the central element. So having that larger central element makes the substance acidic in and of itself. So the trends in general from left to right have to do with the increasing electronegativity of the central element, whereas the trend from top to bottom has to do with the increase in the atomic or ionic radius of the central element. Now this is for the binary substances. Another way to look at it too, and this is a little bit more mathematical, and I'll be honest with you, I probably won't be using the full extent, or maybe won't be using this too much in this class, but I kind of want to show it to you to give you a different perspective in terms of acidity. You could look at the charge square divided by the ionic radius of the substance to determine basically how strong is this H plus associated with the element, right? And the idea is that as this value becomes larger, the substance may indeed become more acidic if you have a polyatomic acid. And generally speaking, that's kind of what you see. If you go from left to right, what you see is that the values get, generally speaking, larger and larger. implying that you have a more acidic substance, and from top to bottom you see, generally speaking, an increase in values. Now, mind you, this kind of complicates the situation a little bit more, and I personally, even though I wrote the table, don't use it all that much. So you could kind of look at this, and if you like it, you want to utilize it, be my guest. But I'm not going to utilize it too much in this course, unfortunately. But what I do use is the table that I'm presenting right here. Now, this is in terms of the oxyacids, the polyatomic covalent molecules, right? So your H2CO3, your nitric acid, your phosphoric acid, sulfuric acid, and so on and so forth. What you see for the substances is that, and actually before I get into the equation, what you see for the substances here is something rather interesting. First of all, let's take a look at the phosphorus analogs, right? You have 2 oxygens, 3 oxygens, 4 oxygens. The pKa is actually getting, a little bit larger for those substances, right? Which is kind of interesting. But take a look at what happens with the halogens here. You have 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. Here the pKa actually gets smaller. And if we look at another analog, we see the same thing. Going from 1 to 2 to 3 oxygens, the value gets smaller. From 1 oxygen to 3 to 4, the value also gets smaller. So actually the phosphorus is a little bit of an exception to the actual rule. As you do increase the number of oxygens, the pKa becomes smaller, meaning that the acid is becoming stronger. And ultimately, the reason that is happening is because having more oxygens makes the central element have a higher positive charge, right? So arsenic with 4 oxygens has a +5 charge. Arsenic with 3 oxygens has a 3+ charge. So you are dealing, in essence, with a much more attractive force of interaction for electrons that are being removed away from the hydrogen. Now, the other thing too that's interesting for the polyatomics is that if you look carefully at what's happening, so let's take a look at HClO4 compared to, well, I guess maybe let's take a look at HClO3, HBrO3, and HiO3. The value going from top to bottom is actually getting larger, generally speaking. And the reason it's getting larger is because the central element, even though it's increasing in size, is not directly bound to the hydrogen. The hydrogen in the oxyacids is bound to the oxygen. So there is a little bit of discrepancy in the size. And the size now doesn't make a big difference. Now it comes down once again to electronegativity. And to kind of summarize the value of the pKa's for the oxyacids, there's an equation, the Pauling oxyacid acidity table. And I don't know why I have 2 I's right there. That's a funny grammatical mistake. So the equation is actually rather simplistic. The pK of the oxyacid is approximated by this formula, 8 minus 5 times the number of oxygen central atom double bonds that you possess. So for instance, let's say that you had 1 oxygen double bond present in your molecule. Based on this equation, the Pauling equation, you have 8 minus 5 being equal to 3. And for molecules that you have only 1 oxygen double bond present, like phosphoric acid or sulfurous acid or chlorous acid, right, the pK is expected to be roughly around 3. And if you look at the actual pKa's for those substances, roughly speaking, the pK is in that vicinity, it's around 3. The one that's a little bit off is arsenic acid. But generally speaking, all these different acids are close to a pK value of 3. Now, if you have 2 oxygen double bonds present in your oxyacid, the equation will tell you that the pK is going to fall in around -2. So now you're dealing with strong acids. And typical examples are sulfuric acid, which has 2 oxygen double bonds, chloric acid, salinic acid, bromic acid. All of them have 2 oxygen double bonds present. And if you look at the table, the values for those specific molecules definitely fall very close to a value of -3 for the species. So it actually looks pretty good for that one. And so the Pauling formula kind of helps you out to get an idea of which acids are going to be stronger. But to make it a little bit more qualitative, the idea is once again that you're going based on the electronegativity of the element. Sulfur is a little bit more electronegative than selenium. Chlorine is a little bit more electronegative than bromine, right? So you have a little bit of qualitative means of describing which substance is going to be a little bit more acidic than the other ones. But notice that there are a little bit of discrepancies. These approximations are rough at best, right? They're not going to give you exact numbers, but it kind of will give you an idea of where you're going to be in the ballpark. All right, so with that, I think I said everything I want to say in terms of trends. So I'm going to stop the video right here, and in the next video we're going to talk about the conjugate acids and bases and predicting your equilibrium shifts.